So he became, in 2007, director of the Max Planck Institute, and he's still director, and at the same time, professor at the University of Heidelberg, and also the leader of the division Stored and Cooled Ions. So as you probably all know, he has been involved in an incredibly number of projects, spokesperson, for example, of isotrap and collapse at CERN, and many more, so I will not mention all of them. But his main research topics concerns ultra-high precision mass spectrometry, mostly with penning traps, also with storage rings or MRTOF devices as well. He also got numerous of prizes recently, for example, this Lise Meitner Prize, also 2 advanced ERC grants, and he's since last year the vice president of the Max Planck Society. So I will stop here because the list is quite long. So I will leave Klaus. So he will talk today about precision mass spectrometry for nuclear physics studies, but also for other topics like neutrino physics, and even also searches for dark matter. So Klaus, I leave you the microphone.
Thanks a lot, Pauline, for the kind introduction, and thanks a lot for the invitation. I see many good friends and colleagues in the audience, at least in the names. I can't see all of them by photo, but I'm very happy that you joined today's seminar. As Pauline has said, I'm happy to talk about precision mass measurements for nuclear and neutrino physics studies. And I thought I'd choose this topic in order to demonstrate on how far one can go with precision nuclear physics experiments. So it's really going to the extremes, and it can only be done because of superb techniques in the field of nuclear physics. At the beginning, I will give a very broad motivation and the fields of applications where precision mass data of nuclear species contribute. I will then explain the basics of PENTATRAP mass spectrometry. Although there are some experts in the audience, I still will give a broad introduction what the techniques are. And then I would show a number of recent results and the future perspectives where I see the field will go to in the next few years. Let me start with that atomic and nuclear spectroscopy can be used as probes for fundamental physics. And I would like to show a few examples where really nuclear atomic spectroscopy can make a deep impact. And what you see here is the first example, namely the variation of fundamental constants, specifically the fine structure constant alpha. The reason for that is that in case that there is a variation of fundamental constants, it means that the energy levels of the electron being in the ground or the excited state might change. And we can use nucleons, nuclear physics, to probe the impact of the nucleus on the energy levels of ground and isomeric state. Of course, no one has ever observed it, but if we can do so by developing sophisticated clocks and looking into these transition energies, that would be, of course, a revolution in our physics understanding. Another application is the investigation and the search for the neutrino mass. We all know that according to our standard model, the rest mass of the neutrino should be 0, but we also know by the observation of neutrino oscillations that that's not the case. So we know already a lag in our understanding of the standard model, and we are looking for that, namely specifically in the decay of tritium to helium, but also in the electron capture decay of holmium, to search for the finite rest mass of the electron or the anti-electron neutrino. And I will show how we can contribute with our experiments to this search. Another application is parity violation, specifically at the moment promoted, for example, for radioactive molecules like radium fluoride, very hot topic also in the interest of the permanent electric dipole moment. And again, if we succeed in atomic nuclear physics to contribute to that field, that would be really amazing. Fifth force search, Pauline mentioned it. I'm going to talk about it as well at the very end, how precision nuclear physics, specifically nuclear mean square charge radii measurements with contribution of nuclear masses, can contribute to the fifth force search or to the search for dark matter. And last but not least, stringent tests of quantum electrodynamics. And I will address a few of these topics as they are indicated here. Exotic systems act as a very sensitive probe to all of these fields. And what I'm specifically talking about are exotic systems like radionuclides, as they get produced for our experiments at the Isolde facility at CERN or at GSI in Darmstadt. As exotic probes, I have in mind antimatter, and I will give examples where we test CPT, the charge parity time reversal symmetry, by comparing the nuclear mass of the proton and the antiproton. And another exotic systems we are going to use are highly charged ions by using an electron beam ion trap, where all but one or all but a few electrons are removed from the electronic shell in order to make the nuclear effects more visible in the study of these systems. When I'm talking about precision nuclear mass measurements, it's mostly about the precise determination of the binding energy. And the reason for that is simple. It's Einstein's equation E equals mc squared. So energy and mass are equivalent. Relation proportion is the speed of light squared. So the mass of the atom is given or mass of the nucleus is given by the masses of its constituents, n times the neutron mass, z times the proton mass, plus z times the electron mass, minus the binding energy. That's exactly the equation that is given here. Now, depending on the precision that one can reach in the precise determination of atomic and nuclear masses, you can probe the binding energy. Either the nuclear binding energy, which is typically in the order of a few mega electron volt over c squared. And to that end, you need relative mass uncertainties of about 10 to the minus 6 to 10 to the minus 8. That's an easy calculation if you take an atomic mass of 100 atomic mass units. So that's about 100 GeV, and 10 to the minus 6 corresponds to 100 keV. 10 to the minus 7 corresponds to 10 keV. That's sufficient to probe nuclear binding energies or nuclear effects like nuclear shell structure, nuclear shell closures, and so on. If you want to probe atomic binding energies, so what is the energy an electron is bound to the nucleus, typically in the order of only electron volts, you have to demonstrate relative mass uncertainties in the order of 10 to the minus 10 and below. And that's exactly the regime I'm going to talk about today, because we are interested in these tiny effects of the nucleus, for example, on the electron binding energies. In order to do so, we would like to store our particles in 3 dimensions in order to have enough time to investigate them until they decay, for example, because they are radionuclides. And in order to do so, you need a radial force to store them in space in a very tiny, finite volume. And the radial force can be created either by electric fields or magnetic fields or light fields. Light fields we don't use in the experiments I'm going to show you today. We only use electric fields and magnetic fields. And this configuration for the storage is called a penning trap configuration. The trapping potential has to be harmonic. And the reason for that is that in a harmonic case, the ion motion can be described by characteristic oscillation frequencies similar to a pendulum clock. And that's in fact the trick of our experiments. We would like to relate any nuclear quantity, that can be the nuclear magnetic moment, that can be the nuclear mass, we would like to relate to a frequency. Also the transition energy can be related to a frequency. And in physics nowadays, the frequency is the quantity that can be measured with highest precision. Last but not least, the precision depends on the volume the particle probes and the trapping potential. And that's the reason for that is if the oscillation amplitude is too large, you accumulate electric and magnetic field inhomogeneities, and therefore you suffer in your precision. However, if you cool, the oscillation amplitude gets smaller and smaller and smaller, so you damp the oscillation amplitudes, and by that you minimize the influence of the field imperfections on your measurement quantity. So what you should take home from this slide is that we have demonstrated single ion sensitivity. So all our experiments at the moment are running with single ions. In fact, we reach infinite storage time if the half-life is long enough. One example is the antiproton, which we have stored for almost 2 years. I come back to that later. A single antiproton stored for 2 years. And we do a frequency measurement for the quantity of interest. Very often we get asked how we compare in our physics and our atomic and nuclear physics with high energy physics. Well, that's rather easy. What you see here is kind of a thermometer. LHC physics happens at around 70 eV at the moment. That corresponds to a temperature of something like 10 to the 16 Kelvin. In our trap experiments, we have energies, particle energies in the order of 1 milli-electron volt, maybe even a little bit below, which corresponds to 10 Kelvin or a few Kelvin in temperature. So these are 15 to 16 orders of magnitude different in energy. And therefore, the LHC is called the energy frontier, while our physics is called the precision frontier. And finally, we put limits on the same physics. Take, for example, CPT. Of course, we are not interested in or not looking into Higgs particle, but we are looking into probes like dark matter searches or CPT tests, charge per universal symmetry tests. So, as already mentioned, the storage of the ions occurred in a penning trap. That's a superposition of a strong magnetic field and the weak electrostatic potential. So the magnetic field lines are the green arrows here. Strong means the typical field strength is about 7 Tesla. And since the Lorentz force equals the centrifugal force, we keep the ion with charge Q and mass M here on an orbit, on a circular orbit. That's a very characteristic frequency. In a pure magnetic field, that would be called the cyclotron frequency. However, the ion can escape along the magnetic field lines, and in order to avoid that, we superimpose a weak electrostatic potential. Weak is here that we apply to these end cap electrodes, typically a few volts up to a few 10 volts. And now the particle is confined in 3 dimensions. The ion motion looks a little bit more complicated as in this animation seen before. So what you have is the axial oscillation due to the trapping potential, purely dependent on the trapping potential. And due to the superposition of the electric and the magnetic field, you get 2 radial motions. One is called the modified cyclotron motion, and the other one is due to an E cross B drift term, which is referred to as the magnetron motion. Here you see a hyperbolic penning trap. You might use either cylindrical penning traps or hyperbolically penning traps. This is a hyperbolic one, where the surface is hyperbolically shaped. You have a few correction electrodes in order to get an as good field adjustment as possible. And this trap would also be used for an online experiments because you see the tiny holes in the end caps that allows to inject and eject externally produced ions like radionuclides into this penning trap. This is how an overall setup looks like. That's the base, the baryon antibaryon symmetry experiment at CERN, where we are interested in the proton and the antiproton mass. You see here the superconducting magnet, 7 Tesla field strength, the cryostat to cool the apparatus down to 4 Kelvin, quite a lot of electronics, and all the sophisticated cryogenic electronics has been developed by ourselves. Here you see a typical trap tower. So this is, in fact, 3 penning traps on top of each other. I come back to that later why we are using that. The reason why I'm showing this photo is that we reach, meanwhile, a machining precision in the electrodes in the order of 1 to 3 micron. And the assembly happens in a clean room. That's why the people wear these gloves here and these clothes. And yeah, you have to be extremely careful not to introduce any dust particle or so in the assembly of the penning trap tower. For today, the only quantity, the only equation of interest is the one given here. That says that the cyclotron frequency, that's the number of revolutions the particle does per second in the magnetic field, is given by the charge Q times the magnetic field strength divided by the mass of the ion. So it's that simple. So by knowing the magnetic field strength, by measuring the cyclotron frequency, you can reduce the mass of the ion. Now you might immediately say, well, I introduced at the beginning that we aim for nuclear masses at the level of 10 to the minus 10, 10 to the minus 11 and below. That would require also the knowledge of the magnetic field to the same precision. That's true. There's no tool at hand at the moment to do so. So what we have to do is we have to calibrate ourselves, the magnetic field, by measuring the cyclotron frequency of a known mass, and that's ideally 12 carbon. So we do a calibration with 12 carbon of the magnetic field, then we measure the unknown mass of the species of interest, and then we do another calibration. You might have noticed here that in this plot here, nu c is not given. There are 3 frequencies given, but not nu c. That's correct, but there's a relationship between the quantity of interest, the cyclotron frequency, and these 3 motional frequencies, the modified cyclotron, axial, and magnetron frequency. This is called the invariance theorem. So even in a non-perfect alignment of the electric and magnetic field, this equation still holds. So by measuring these three frequencies here, we get the true cyclotron frequency, our quantity of interest. And that we are doing in a non-destructive way. So we can keep our particles stored while we measure the revolution frequency. And that's shown in this animation here. So this is now a top view of the ring electrode of the penning grab. It's fourfold segmented. This is, of course, simplified the particle motion. And it induces, since this is an oscillating charge, it induces a tiny current on the surface of the electrodes. Tiny, it's in the order of 1 femtoampere, 10 to the minus 15 ampere. But it can be measured as a voltage drop across an impedance, which becomes in resonance a real resistance. And so what you see here, this is the voltage as a function of time. You see this oscillating mode, and the signal is about 1 femtoampere, and then you do the fast Fourier transformation, and then you get the frequency spectrum. That's exactly what we are interested in. And of course, you need a very sophisticated electronics. All is based on 4 Kelvin. So it's a helical resonator to do a resonant amplification of the signal. That's a cylindrical coil made out of niobium titanium for the axial oscillation. You see here our home-built cryogenic low noise amplifiers. Cryogenic because they are operated at 4 Kelvin. Low noise because this is now for the experts. The current noise is about 1 femtoampere per square root hertz, and the voltage noise is about 100 picovolt per square root hertz, so incredibly small numbers. And this is the overall electronics that's needed, a lot of filters at several stages, 4 Kelvin, 70 Kelvin, and 300 Kelvin stage, and so on. Here the proof that we can really see individual ions. This is the signal of 7 individually stored, of 7 protons stored in the penning trap. So this is the signal of 1, 2, 3, 4, 5, 6, 7 protons. And you might now say, well, all the protons should have the same mass. That's correct. So why do they appear at different positions in the frequency window? Well, the reason for that is that our trapping potential looks like that. I hope you can see now my video. And the particle, since they are charged particles, they do Coulomb repulsion. So they sit at different orbits in the penning trap. And since they sit at different orbits, they see slightly different magnetic fields because of the magnetic field homogeneity, and therefore they have different revolution frequencies. That's not good. We have to get rid of 6 of them, and that we are doing in a kind of an evaporative cooling technique. So our trapping potential gets slowly lowered until the hottest particles escape and only one particle, one proton remains. And you see now a real-time video. I hope it works. You see that now we remove one proton after the other. There are still 5 in. They come closer because they get colder and colder. It's evaporative cooling. There are still 2 in. Now the second last one gets removed. And now we remain with a single proton in the trap. So that's really a real-time video. After a few seconds, we have prepared a single proton in a penning grab. And already what you see here is about a 10 to the minus 8 proton mass measurement with this single spectrum that we have observed here, simply by taking the frequency and knowing the magnetic field strength. This is how an overall setup looks like. I have already introduced that, and this is an apparatus that has been used for the mass measurement of the proton and the antiproton to perform a CPT, charge parity time reversal symmetry test. And with that, I would like to jump into a couple of results. And I start with the masses of the building blocks of matter and antimatter, namely the question, how heavy is a proton, how heavy is an electron, and how heavy is an antiproton, which is the lightest nuclear particle we have. And these experiments have been performed either at CERN, at the AD facility, or here at MPI in Heidelberg. So the way to measure the proton mass was that we stored a proton while using 12 carbon as the reference for the magnetic field calibration. The problem is you would like to have your balance, your reference mass, as close as possible to the one of proton, which is not so easy, because in fact the proton is the highest charged particle you can get. The proton has the charge to mass ratio of 1. And the closest you can get is by using another particle that has 1/2, like 12 carbon 6+. So you remove all electrons to have a bare 12 carbon nucleus. It's still a little bit unbalanced, which causes systematic uncertainties, in fact, but it's already getting close. So you calibrate a magnetic field with 12 carbon 6 plus. Of course, you have to correct for the missing binding energy and of the electrons and the missing electrons itself. And you compare that, so you use that as a calibration, and then you measure the proton mass, and then you do again the calibration. So this is the frequency ratio that gives you then the mass ratio of the proton to 12 carbon 6 plus. We have done so 3 years from back, and we obtained the most accurate proton mass in the world. So if you open up the CODATA 2020, it's exactly this value that's given here for the proton mass, with a relative uncertainty of 3 times 10 to the minus 11. And the uncertainty is given by the statistical uncertainty, simply how narrow you can make your resonance and how well you can fit that resonance. In fact, meanwhile, we are doing phase measurements. It's not only that we count the number of revolutions, we even count whether it's 1 million revolution plus 5 degree plus 10 degree, which we call the phase measurement technique. But the main uncertainty comes from a systematic uncertainty, namely 12 carbon 6 plus is charged, is 6-fold charged. And unfortunately, there is a shift which is called induced image current shift. So the particle, when it oscillates in the traps, sees its own image current and gets distorted. And that effect is, of course, stronger for the 12 carbon 6 plus particle than for the proton. And this causes a tiny systematic uncertainty at the level of 3 times 10 to the minus 11. We know how to get rid of it, namely by increasing the trap size. This effect scales with the third power of the trap size. So by doubling our penning trap, which is typically an inner diameter of 5 millimeters. So by doubling this from 5 millimeter to 1 centimeter, we would reduce this effect almost by an order of magnitude. And that's what we are going to do right now in order to go down here to the level of about 1 to 3 times 10 to the minus 12. How has the proton mass evolved over the last 200 years? I have a marvelous student called Fabian Heise, who's also interested in physics history. And he digged out close to 200 publications on the proton mass, even going back to the year 1812, where gravimetric stoichiometry was used to determine the proton mass, at the time with a relative precision of about 10 to the minus 2. And then in the beginning of the 19th century, it was single focusing and double focusing spectrometers by Aston, for example, who pushed the limit down to 7 times to the relative precision limit to 10 to the minus 7. And then mass synchrometers as used by Dave Lunny, for example, Mistral. And then later on in the year 1985, it was Demelt who introduced the penning trap for ultra precise atomic and nuclear mass measurements. And that pushed it down to the 10 to the minus 10 regime. And then we introduced this phase measurement technique that allowed us to go down to 10 to the minus 11 or even below, as you will see later. So this is the present status. It's amazing progress over the last century in the precision of a nuclear mass. As mentioned, we could use the same technique to measure the antiproton mass and to perform a stringent test of charge parity time reversal symmetry. So instead of using now 12 carbon as a reference, since we have already measured the proton mass, we can simply compare the antiproton to the proton mass. In fact, it's not that easy. And as you can see here in this simplistic sketch, we didn't use the proton, we used the H- particle. So that's a proton with 2 electrons attached, and compared the H- mass to the antiproton mass. And you might think about why we did so. So we didn't use the proton and compared it to the antiproton, but we used H- ion and compared it to the antiproton. Remarkable about that experiment is that, as already mentioned, the temperature is liquid helium. So it's 4 Kelvin, it's even a little bit lower. We are able to reduce by electronic feedback the particle temperature to a few hundred milli-electron volts. Sorry, a few hundred millikelvin. The pressure in the experiment is below 4 times 10 to the minus 19. And you might wonder how we know that. Well, the antiproton has been stored, as already mentioned, close to 2 years. So a single antiproton stored for 2 years. And since the annihilation cross-section of antiproton and hydrogen is known, you can estimate the number of background particles in the volume of the trap in order to have a survival time of 2 years. and that ends up in an upper limit of 4 × 10⁻19 millibar. I guess it's the world best vacuum on Earth, or at least measured on Earth. Storage times years. So what we did is we measured the cyclotron frequency of the antiproton to the H-I in a couple of thousand times. So we measured the revolution frequency of the proton, antiproton, we moved it away, we put in an H-I and compared that over day and night, over days and weeks. And by that, we obtained 6,000, 6,500 individual cyclotron frequency ratios of these two species. You can plot them in a histogram. It looks beautifully Gaussian here. And from that, you can deduce the charge to mass ratio of the antiproton to the proton, which you assume to be 1 if CPT theorem is right. And that's exactly what we get. We get a -1 point, and now comes 11 zeros and then a 1 with a 69 uncertainty on the last digit. So that's a 7 × 10⁻11 test of CPT symmetry, which is on the baryonic sector, the most stringent test of CPT symmetry. I know that there is, for example, the kaon sector, including strangeness, where there is already a test at much lower limits, but you never know where CPT failure might occur. And we should also not forget that we have to look into the energy regime and not only the charge to mass ratio. Nevertheless, it's the most stringent test on the baryonic sector of CPT symmetry. It's not that easy. As mentioned, we are using H-ions. So in order to deduce the proton mass from that, we have to correct for the 2 additional electrons shown here. We have to correct for the binding energy of the first electron and the electron affinity of the second electron attached to it, therefore the H-. And you have to correct for the polarizability, because the 2 electrons, they like to move in a kind of a correlated orbit. And therefore you have to correct for the polarizability. That gets done in kind of a dark analysis, so blind data. We added an offset at the very beginning, who only a third person knows about this offset, and only at the very end, we take this offset away from the frequency, and then the final result gets published. That is this result here. We did similar experiments by measuring the electron mass, and by that we were able to, that we already did a few years ago, and therefore I don't report here on that. Nevertheless, we are now keeping the world record in the CODATA table. For the electron mass, we improved the previous best value by almost a factor of 13. This is the uncertainty given here of the electron mass. We improved the uncertainty of the proton mass by a factor of 3. So now you might ask, well, are they also able to improve the neutron mass? Yes, indeed, that's our idea. In order to improve also the neutron mass, we do a tiny trick, because of course we can't store a neutron in our penning trap, but we can store the deuteron. And since the binding energy between the proton and the neutron is known, and or can be measured to a certain uncertainty limit, by measuring the deuteron mass, you can deduce the neutron mass. And that's exactly what we did, published last year. That's the world best mass of the deuteron. And from that, we could also extract the neutron mass and made a 20% improvement on the neutron mass. Not so much, but still we keep right at this moment the best value for the proton, the electron, and the neutron. So all building blocks of matter are based on frequency measurement in a penning trap. With that, I would like to move on to some heavier species of interest for neutrino physics and the contribution of nuclear masses to neutrino physics. I already mentioned that we are specifically interested in the decay of tritium to helium-3 with a release of the neutrino and an electron. And just last year, 1.5 years ago, the Cadmium collaboration, the tritium neutrino mass collaboration, released the best value of the upper mass limit of the anti-electron neutrino of 1.1 electron volt over c². And my department is a member of the collaboration of the Cadmium experiment. We contributed, among others, the penning traps for the best gas analysis, and we contributed the real gas window. Okay, how do nuclear masses play a role here? Well, the maximum energy that is available in this decay is simply given by the mass difference of the mother and the daughter nuclei. So of course, this Q value or upper mass limit can also be deduced from the Curie plot by fitting the endpoint spectrum. But you can also use the externally measured Q value, mass difference of the mother to the daughter nucleus, to investigate systematic uncertainties. And that's exactly why we are interested in the measurement of the tritium and the helium-3 mass. That has already been done quite a few years ago by Ed Myers. That's the second group in the world that does this ultra-high precision mass measurements at Florida State University. But there is at the moment a problem which is called the puzzle of light atomic masses, which I would like to introduce here. So although talking about ultra-high precision, there are still problems that needs to be solved. And let me build it up slowly. So as already mentioned, we are measuring, or we measured the proton mass or the hydrogen mass in relation to 12 carbon. That's the 3 times 10 to the minus 11 measurement I reported before. Also, the deuteron mass has been measured by Van Dyck, but also by us, to 12 carbon as the reference. However, the helium-3 and the tritium Q value has so far only been measured against the HD molecule, never against 12 carbon, so only against the HD molecule. And the present best value of, with an uncertainty of 70 milli-electron volt on the Q value has been deduced by Ed Myers from the comparison of the 3 helium mass and the 3 tritium mass towards the HD molecular mass. And just a few years ago, Van Dyck measured 3 helium against 12 carbon. And that is nice because now we can make a consistency check by looking what is the outcome here, namely by adding the binding energy of the deuteron and the hydrogen atom and extracting the HD mass. And we can do the same here. And we can now compare if you get the same numbers. That was done as a systematic check. And the outcome was that there is a 5 sigma discrepancy. The molecular mass that used from these measurements here compared to these measurements here deviate by 5 sigma. And that's a lot. For us in the field of precision, atomic and nuclear physics, let me say that's a disaster. A 5 sigma discrepancy, it's really a lot. And we had to figure out why it is that much. That was one of the motivations, by the way, why we measured the deuteron mass. It was not only to deduce the neutron mass, but it was really also to cross-check this link here. That's what we did at the level of 9 times 10 to the minus 12. And that already reduced the deviation to 2.4 sigma. So from that it was obvious that the previous deuteron mass was wrong by a certain factor. And right now, we just started a few weeks ago a measurement campaign to measure also directly 3 helium against 12 carbon 4 plus. That's again a mass doublet. 3 helium Q over M of 1/3, and 12 carbon 4 plus has also 1/3. And the same we do with tritium. Tritium 1 plus has the Q over M of 1/3, the same as 12 carbon. So that's a perfect doublet. We would like to see how then the Q value is and to provide it to the Catron collaboration, hopefully with a 20 milli-electron volt uncertainty out of 3 GeV. That's a 4 times, 5 times 10 to the minus 12 measurement. To give you an easy image of our precision regime, whenever I talk about 10 to the minus 11, it's hard to imagine what that means. I used as an example the Eiffel Tower. I think it's known to everyone. It has a weight of 7,300 tons. I looked it up once more. That is 7.3 times 10 to the 12 milligram. With our technique, we would be able to measure whether a bee of 60 milligram has landed on the Eiffel Tower or not. That's exactly the difference of 8 times 10 to the minus 12. That's what we have demonstrated, of course, achieved on the atomic scale. And right at this moment, we are running an experiment where we have improved the apparatus and hopefully reach between 1 and 3 times 10 to the minus 12. That would allow us to measure whether an ant is sitting on the Eiffel Tower or not. Of course, on a microscopic or on the atomic scale. Going even heavier, this was about the neutrino mass by looking into the decay of tritium and deducing the anti-electron neutrino mass. But we came up with the idea that we could do similar experiments, but looking into the neutrino mass. And that you can only do by investigating an electron capture decay. And the nuclide of choice is 163 holmium, which captures an electron from the electronic shell towards an excited state of 163 dysprosium with the release of an electron neutrino. This holmium can be embedded in a metallic magnetic calorimeter, and you do a calorimetric measurement of the released energy from the excited state of the 163 dysprosium nucleus. And by that, you can measure the fully released energy in this decay. And then the missing energy, if you compare that to the Q value, again, the mass difference of the mother nuclide and the daughter nuclide, gives you a hint for the electron neutrino mass. Very similar to the tritium decay, but this time now for the holmium electron capture decay. This is how the spectrum looks like. So you get a continuous, because it's a three-body process, you get this continuous spectrum with a clear cut here at the endpoint. That's the maximum energy available for this decay, which is given by the mass difference, the nuclear mass difference of 163 holmium and 163 dysprosium, which at that time when the experiment was launched was assumed to be around 2.5 keV, 2.57 keV. You need the Q value with an uncertainty of something like 3 electron volts to be competitive to the Cutran experiment. That is 163 GeV with an uncertainty of 3 electron volt. That's again in the low 10 to the minus 11 machine. And if you look into the literature for the Q value of this electron capture decay, the accepted value by the atomic mass evaluation in a few years ago was in the order of 2.57 keV, as mentioned before. It's, by the way, the lowest energy decaying nuclide for an electron capture decay, 163 holmium. But there have been already some indications that this value might be wrong. For example, metallic magnetic calorimetry published this value here in 2014. That triggered us to look into the system by doing for the first time a direct holmium to dysprosium Q value mass difference measurement. And this is our result in perfect agreement with this one. So it's obvious that there has been a mistake in one of the former measurements. It's hard to tell. Probably the decay was into an excited state and they missed some energy. We don't know exactly, but that's how it looks like. And recently, again, by metallic magnetic calorimetry, another measurement was done, and they are now in perfect agreement with an uncertainty of 30 electron volts, but it's now shifted up by almost 300 electron volts to 2.85 or so electron volts. Right now, we are running an experiment with 163 holmium together with Uli Köster from the ILL in Grenoble, with Klaus BLAUM from the University of Mainz, in order to improve this Q value down to 3 electron volt, or hopefully even below. How do we do that? We plan to do so with an experiment called PENTATRAP, installed here at the Max Planck Institute for Nuclear Physics in Heidelberg. And PENTATRAP already indicates that we are going to use 5 traps on top of each other. In the introduction, Pauline mentioned that they are very happy in Bordeaux that they managed to get the 1 penning trap into operation, and congratulations for that. And then Bertram asked, what about the second penning trap? Pauline said, well, that's difficult. Indeed, to run 2 penning traps is difficult. We would like to run 5 on top of each other. And the motivation for that you will see soon. This is the equation mentioned in the introduction. The frequency is given as the charge to mass ratio times the magnetic field strength. And the B field, that's the problem. That you have to know to very high precision. And typically it's unknown, so you have to calibrate that. The reason, or the way we are doing that is that we use a reference mass given by a second ion. And with this trap tower, if we have 3 traps, we do not have to reload all the time. We simply shuffle the 2 ions up and down. So this is the ion 1, this is ion 2. 1 acts as a reference ion, so that could be the proton, that could be the 12 carbon ion, or that could be holmium, that could be dysprosium. And we always measure in the same trap at the same position. That cancels out the magnetic field when we assume that there is no time variation in the magnetic field. If the magnetic field would be constant in time, that would be the perfect method to do so. And you see, if we measure the cyclotron frequency of one species compared to the other one, we could do a polynomial fit. And then we measure the frequency ratio of these 2 and we get the mass ratio. Yeah, of course, right, by saying, well, This takes some time, in our case, typically 5 minutes. That's the time we need to swap between the two ions. And during that time, the magnetic field might change because there is a time variation in the magnetic field. To that end, we introduced a third trap, using a third trap as a measurement trap. Now we could measure either here or here, and we measure now in parallel. And that allows us to see whether there is a time variation in the magnetic field. So we measure at the same position between these two species or at the same time between these two and these two. So that's the idea behind, and that calls for 4 penning traps. And simply because of symmetry reasons, we added a 5th penning trap. And that even allows us to use this 5th penning trap for monitoring trap, for example, by storing an electron, the proton here, and then we can do an in situ magnetic field calibration and observe the magnetic field all the time. That has not yet been implemented. The trap is there, but we didn't use it so far. So far, we use only these 4 penning traps, and I'm going to show the first results, namely by looking into another neutrino physics interesting case, namely rhenium to the decay of rhenium to osmium, which was also proposed for an upper limit of the anti-electron neutrino mass by the beta decay of 187 rhenium, for example, by the Mare experiment. And that's how the decay spectrum looks like. The trick with PENTATRAP is that we are going to use highly charged ions. Why is that a trick? Well, the cyclotron frequency scales with the charge state Q. So while the resonance width stays constant, you can increase the frequency with the factor of the charge state. So by going to charge state 30 plus, you can boost your precision by a factor of 30. That's exactly the trick we are going to use. Of course, it makes it a little bit more complicated. You need very good vacuum, 10 to the minus 15 millibar and better, but we have demonstrated that. That's the reason why we are going to highly charged ions. Of course, if you want to know the neutral atomic mass, then you have to correct for the missing electrons, for the mass of the missing electrons, as well as for the missing binding energy of the electrons. That can be substantial in the case of a charge state 29 or 30 plus. This is this equation here. So how did we do the experiment? Rhenium versus osmium. This is a simplified sketch of our penning trap. This is the first configuration, rhenium, osmium, rhenium. We swap them simply by moving them around. That takes typically a few minutes. In that case, we changed every 30 minutes. We measured the frequency ratio via phase detection technique. We do that for a couple of days, and then we deduced the mass difference between rhenium and osmium at the level of, in fact, we succeeded to do so at the level of 6 times 10 to the minus 12. This is how this frequency spectrum behavior looks like, position 1, position 2, or vice versa. From that, we can deduce the atomic masses at the level of 6 times 10 to the minus 12. That's the highest precision ever achieved on a nuclear mass. And we just submitted it last week to Physical Review Letter. However, when we did that experiment, we got puzzled at the very beginning, because in order to avoid systematic effects, we reload the trap every 2nd or 3rd day, simply to make sure that we don't have day-night effects, or we might have a contamination in, or maybe decay occurred or so. And in order to avoid that, we simply reload the trap. So we put in new rhenium and osmium species. We did that about 30 times. And in half of the cases, we measured a certain frequency ratio for the mass difference, or for the mass ratio of rhenium to osmium. And in the other 50% of the cases, we got a value which was 200 electron volt off. And that puzzled us a lot. So how can it happen that you load all the time rhenium and osmium, and the frequency ratio is different exactly by 200 electron volts from one to the other measurement? Of course, we thought about systematic effects like problems in the triggering, all that what you know from the nuclear physics experiments, problems in the timestamp and so on. We couldn't find the reason. And then we thought, okay, what about making unity measurements? We always measure osmium against osmium. We believe that they are all identical heavy, and we do then the same for rhenium against rhenium. Reload the trap with 2 new rhenium species, and you measure the ratio. That should be 1. In fact, that was the case for osmium 29 plus against osmium 29 plus. but not the case for rhenium-29 plus towards rhenium-29 plus. Sometimes we got unity between two rhenium species, and sometimes we got the difference by a very tiny fraction of only 10 to the minus 9. Almost nobody would be able to see that, but with our really ultra high precision measurement, we were able to detect that. It's a difference of 200 electron volts. And then it immediately came to my mind what the reason could be, namely isomeric states. You might now say, of course, isomeric states, that's long known, of course, in nuclear physics. But what I'm talking about is an atomic isomeric state. And that's exactly the case. So in the case of rhenium-29 plus, the remaining electrons can be in two stable states. I have to introduce now a little bit of atomic physics theory, namely rhenium-29 plus, or osmium-30 plus, it's exactly the same, has an electron configuration that belongs to krypton plus 10 electrons in a 4D shell. That is the assumed to be ground state, which is a stable, highly charged ground state. However, you could also have a configuration where one electron is sitting in a 4F shell. And the excitation energy is exactly 200 electron volts. And this is a highly forbidden transition of this very last electron. It's a 5-fold forbidden transition with a half-life of more than 300 days. So the electron simply sits in this excited isomeric state and remains there. And that's exactly what we measured. And when I approached the theory colleagues and asking them, can you calculate this isomeric state, this isomeric atomic state? Among others, I asked Paul Indelicato from Paris. He did so. And if you see, our experimental value for the excitation energy is 202.2 electron volts with an uncertainty of 1.7 electron volts. And these are the theory values. Zoltan Harman from the institute here, Paul Indelicato from Paris, and Maurizio Sauberkort from the University of Heidelberg. There's an amazing agreement, not only between theory, but also with our experimental value. And that was then the hint. We did the same with osmium-30 plus. We also observed this isomeric state there. So that was the clear proof. Why I like this experiment so much is that we are able now to look for suitable clock transitions. You might remember in my introduction, I mentioned that you might be interested in looking for the time variation of fundamental constants. That requires really ultra high precision clocks. And it's now this nuclear physics experiment that allows to provide such a clock. Of course, the energy is very unfortunate. 200 electron volts is not good. You need to excite it with a laser, so that's not good. But if that transition could be used, since the half-life is 300 days, it would improve our present best clocks by 6 orders of magnitude. So the present best clock is at 10 to the minus 18 stability. We could do it at 10 to the minus 24. That would be really amazing. Unfortunately, this transition is not good. But right now, we are looking in other transitions that might be better suited. For example, there's one in uranium-19 plus with an excitation energy of 8 electron volts. That would be a perfect transition. And we have to see how the half-life is and so on of this electronic state. With that, I move to the last topic in the last 3 to 5 minutes, namely nuclear masses for fifth force search. And it's again nuclear spectroscopy that can do here a really important contribution. And I start with the investigation of the nuclear charge radius by high resolution spectroscopy. The reason for that is that the isotopic shift can be measured with lasers with very high precision. And the isotopic shift might be sensitive to fifth force. And the reason for that is this equation here. So this is the isomeric shift. This is the isotopic shift, which depends on the field factor times the mean square nuclear charge radius, the change in the mean square nuclear charge radius, plus an atomic mass factor. This is what we can contribute by precision nuclear mass measurements. This has to be done by precision laser spectroscopy experiments. If you plot two transitions against each other, this is then the so-called King plot, which is assumed to be linear in first order. Any deviation from this linearity might hint towards fifth force, because if there's a new force mediated through scalar field with a certain mass m phi, it might act on the neutrons. And let's take, for example, calcium 40, 42, 44, 46, and 48, which has different neutrons by almost a factor by almost 20%, going from 20 neutrons up to 28 neutrons. The new force mediated through scalar field might have a different impact on that. And you might see a tiny difference in this linearity behavior. So you see a non-linearity. Of course, you can immediately argue, and this was proposed, by the way, by Julien Berengut and by Victor Flaumbaum, for example, to look for these non-linearities. You might immediately say, well, if there's a non-linearity, it's probably nuclear structure effects. I fully agree. But as long as you don't see a non-linearity, then you can argue that this sets new limits on the fifth force. And that's exactly that has happened. And what it requires is high precision atomic and nuclear spectroscopy measurements. Among others, it requires ultra high precision nuclear mass data in the isotopic chains of calcium, strontium, and ytterbium. These are the three best cases known so far because they have very good accessible laser transitions. And most importantly, they have 4 stable even species because you would like to avoid hyperfine structure. Calcium, you have calcium 40, 42, 44, 46, and 48, for example. And in order to demonstrate that we can do the mass measurements at the level of 10 to the minus 11, that's namely required, we did such experiments on xenon. Xenon was very easy to produce for us because we used a gaseous ion source. And it has 5 even stable species, namely 126 xenon, 128 xenon, 130, 132, 134. This is the abundance. And you see even a low abundance isotope like 126 xenon with a natural abundance of only 0.1%, we were able to measure. In fact, we measured all of them with an uncertainty of 8 times 10 to the minus 12. We improved on the lowest abundance isotopes almost by 3 orders of magnitude. And by the best known species, we still improved by a factor of 4 to 7. By that, we demonstrated that we can really contribute here to fifth force search or to dark matter search by providing the nuclear masses of these species. And hopefully by end of this year, we are able to run first ytterbium because that's the most promising case for this dark matter search. With that, I'm at the end of this colloquium. I hope I could demonstrate that precision PENTATRAP mass spectrometry has reached an amazing precision even on exotic systems, on radionuclides, long-lived species, but also partly short-lived species, and has opened up many new fields of research in neutrino and nuclear physics experiments, something we have not dreamed of maybe 10 years ago, but now we have reached it and we have demonstrated it. With that, I'm at the end. I would like to thank, of course, all my colleagues in my department. They are really marvelous people that have produced the data I just mentioned to you. And also thanks a lot for the invitation and thanks a lot for your attention. Thank you.